Hi, thank you so much. I'm Paul, and I'm presenting joint work with Gerdus and with Ariel. This picture here is showing the current House of Representatives in this country. And these women and men have the task of representing the American people. That being said, already at the first glance, you might be able to see that this picture does not look representative of the American population. And there are multiple ways in which this is the case. For instance, it is very well known that women are underrepresented in the House. They make up for slightly less than a quarter, even though they have more than half of the population overall. Similar things can be said for age groups, for example, where it is well known that younger groups, especially groups under 35 years of age, are drastically underrepresented, which makes it somewhat encouraging that some of the children are also being sworn in, apparently. So maybe that's going to change, but for the time being, the House is much older than the population overall. These demographic groups are what we usually think about when we think about groups who are not accurately represented in the House. But here's another group that I worry about just as much. These data are for the last House of Representatives, but 53% of the members could be labeled as skeptics or outright deniers of man-made climate change. At the same time, polls revealed that only a clear minority of the population harbored these views. And this has very clear and very direct policy implications when it comes to approaches that are meant to combat climate change. So in general, this is something that I worry about, that there's some opinion or some conviction, some value held by some part of the population. The previous two slides showed you, hopefully, that members of the House are not typical American citizens. They're very, very special American citizens. And so just because some fraction of the population holds a view, that doesn't have to translate into anything in Congress and doesn't have to translate into policy. So before I even tell you what framework we're operating in, I would just like to fix this high goal to more accurately represent unknown groups in the population. And this unknown here is key, because if we only cared about climate change deniers, we could try to impose a quota. If we only care about women, we absolutely can impose a quota. But these opinion groups are particularly tricky. They're somewhat hard to elicit. It's not really clear which opinions will become relevant over the tenure of a Congress by the time that we vote on it. And finally, even if we knew about all these opinions, there are just so many, we can't impose quotas on all of them. So can we still somehow make progress on all these fronts at once? That's what this paper is about. The framework that we're operating in is known as sortition. So I will begin by telling you what sortition is and why we believe that it's really exciting. And then I will talk about the means that we apply, namely stratified sampling. And we hope to use stratified sampling to get somewhere close to this goal in the context of sortition. And then finally, I would like to share an experiment that we did that aims to show that our theoretical findings actually have some direct implications for practitioners of sortition. Sortition is a paradigm of representative democracy, which means that in addition to the people down here, we also have a smaller body of representatives that has the ability to discuss with each other and exchange ideas freely. But in contrast to other paradigms, these people are not elected. Instead, they're just randomly drawn from the population. This method has an extensive historical background. I don't have the time to get into that. So I would just like to share a present-day experiment that hopefully gives some credibility to the fact that this is indeed not a crazy idea and is something to be taken seriously. Oh. These people here are members of the Irish Citizens Assembly. They're 99 random Irish citizens, and they convened between 2016 and 2018 over 12 weekends to discuss multiple topics of societal importance. And by far, the most prominent of these topics was whether abortion should be legalized in Ireland. They were not selected for any prior knowledge, so they spent a lot of time reading informational material. They met with experts from academia. They heard of people who had personal experiences with abortion, say. And finally, they made a set of recommendations to the parliament there. And the parliament passed on the recommendation, in particular the recommendation for abortion to legalize abortion up to the 12th week. They passed it on to the population. It passed by 67% in a referendum. And so now the constitution has been changed, in part thanks to these people. And I looked through some of the material that this assembly produced, and I'm just deeply personally impressed by the level of ownership that these people from all walks of life have over very, very fraught and very nuanced and complicated topics. So this is why now there's a growing coalition in the political sciences, but also among political activists who try to explore sortition further and make that another way that we as citizens can participate in our democracies. How can we think about that in a more mathematical way? Let's say that the square to the left represents the population. And some subset of that population holds some view m, the other half doesn't. And at the same time, we have this panel, say, with 6 seats. So we draw 6 random people from the population, and obviously we can count how many of these people come from the subgroup M. Say 4, and we call this random variable U sub M. Now, a very nice property is that as long as we make sure that every person is selected with equal probability, the expected value of this variable is just the share of M in the population, M over N, times the size of the committee, K. And this is a very strong contrast to the examples that I started this talk with. Gross and systematic underrepresentation of, say, women or young people will never happen in such a system. And this guarantee holds for any possible subset M of the population. This is very strong. That being said, of course, the guarantee is only a priori. And in particular, in this example, we drew 4 members from M, even though we might have wanted 3. This is the distribution. It looks very binomial-like, even though, technically speaking, it's hypergeometric. And these distributions are somewhat wide. It would be nice to just say, okay, we will just blow up the size of these committees until the variance doesn't matter anymore, but this is not possible due to logistic reasons. And so people in practice do worry that in a sortition experiment, they might draw too few women or might draw too few people from one specific region. So what they do is that they stratify, say by gender or by region. Say we stratify by gender. We split up the pool of voters into women and men, and we reserve 3 of our seats in the panel for women and 3 for men. Now we can again draw 3 men and 3 women. We can again denote the number of people who end up on the panel and came from M by A sub M, say. And the guarantee that we had before still holds. Every person is still selected with equal probability, so the expected value is still fair. But this time, well, I drew that somewhat suggestively. There was a high correlation between M and between gender. And also we somehow got lucky and drew exactly 3 out of the 6 people coming from M. This is not a pure coincidence, of course. If we look at the distribution, we see that the distribution became narrower. The variance decreased due to our stratified sampling. And this is really cool because we didn't even think about M when we stratified. We thought about representing women well, and suddenly we're making progress on this opinion M. That being said, okay, we got really lucky in the way that this correlation fell. Can we also get unlucky? And it turns out we can get somewhat unlucky. We can actually make this distribution broader, but not really. The worst case would be if there's no correlation at all between gender and between M. And in this setting, this is what the distribution looks like. It's very hard to see the two distributions here, so let's zoom in a bit. And now if you squint a lot, you see this blue bar here on the top, which hints at the fact that uniform sampling gives us a slightly sharper distribution, but this is near invisible, and will be really, really invisible if we have larger sizes than in this distribution. So the hope is that this observation can be generalized, that we stratify based on reasonable features, and then most opinions that come along will somehow correlate with gender, with race, with income. And so hopefully we will get these effects that make the distribution narrower and decrease the variance. And even if we get really unlucky and something doesn't correlate at all, then still, hopefully, it generalizes that we essentially can't lose anything and can't blow up the variance. If we lived in a continuous world, everything would be cut and dried. Continuous here means that the voters come from a continuum. In this setting, it's very well known that if we stratify, we can only decrease the variance, never increase it. We happen to live in the discrete world, though. So there are 2 major complications. The first one is that now we have to draw without replacement. And this is exactly where this slight widening of the distribution came from. It's not a big problem. The bigger problem is that we also need to deal with rounding, namely deciding how many seats should be allocated to a stratum might not be as straightforward as in this example. It was very convenient that I implicitly assumed that women and men both had exactly half of the population, and also that the number 6 is divisible by 2. If this is not the case, we somehow need to randomly round, And because we're looking at variances, this really risks that we introduce new variants that can completely blow off the somewhat delicate balance that we had in the bound earlier. We propose a way of rounding, which we call block rounding, that still guarantees that every single person is selected with equal probability, and whose variance behavior is very nice. It dovetails very nicely with the places where the bound is somewhat loose, and it doesn't increase any variance when the bound is tight. And with that, we're able to show our theorem, namely that under this block rounding regime, and with a very innocuous assumption on the size of the strata, the variance of stratification to the left is indeed bounded above by the variance of uniform stratification, uniform sampling, I'm sorry. That is, except for this factor of n minus 1 over n minus k, which fortunately is not a big problem. So in the island example, for example, it's 1.00003. And in all other examples that I'm aware of, this constant will be very, very close to 1. So morally speaking, it still holds that we can only win through stratification and not lose. I should also mention that we have a generalization of this theorem where we give bounds on the actual reduction in variance if we stratify well, and that all these analyses are tight. What does this tell us for actually stratifying? Well, a couple of things. First of all, it's good to stratify very finely, essentially up to the point where every stratum is only responsible for one single seed, because up to then the theorem from before holds, and we can only win, not lose. Then we want to make these strata very homogeneous so that any opinion that we can think about probably will split them very unevenly. Maybe everyone is on one side of the argument or everyone is on the other side of the argument, but it's somewhat unlikely that an opinion will actually split them halfway through. This is what we have to keep in mind if we want to stratify that, and we can make that formal, of course. And finally, our block rounding makes use of an ordering of the strata, and it pays off to place similar strata next to each other because it reduces the variance introduced by rounding. All of that was just for some abstract subset M of the population. What if we actually care about opinion groups? Can we show something then? We want to show that we can indeed apply what we learned in theory to a setting that cares about opinions, about real opinions of real people. So we looked at data from the General Social Survey from the years 2014 and 2016, which have sample sizes of 1.7 thousand and 2,000 people approximately, and our panel size is set to 50. Now, we have all these agents and we have all these features about them. We labeled 14 of the features as demographic features, and this is quite extensive. We have age, education, religion, race, income, most things that you might think of. And then we have more features that we labeled as political attitudes. We turned these attitudes into binary features, and they concern different areas of politics. It's somewhat orthogonal. And so, for example, the examples here would be, is it ever okay for a policeman to hit a man? Or should the government do more to combat wealth inequality? Or should we pay more for natural parks? So it's quite diverse. And now one of my collaborators received the demographic features and a random subset of the binary attitude features to get some feeling for this data set and for this population. And he was responsible for building a stratification that was supposed to perform well on the non-revealed attitude features. And yeah, we want to build this process really to model how a person who does a sortition experiment has to stratify if they don't know yet what this panel will discuss. Yes. We made them binary because that then defines an actual subgroup, subset of the population. So the original features were not binary, but we set a threshold somewhere. Thank you. We compare a manual stratification, the baseline of no stratification at all, so uniform stratification if you want, and then a very simple stratification just based on demographics, and an approach based on k-means clustering. We compare them with respect to how much they reduce variance on these non-revealed features, which can be expressed very naturally instead as an increase in panel size that we would need to get the same benefits just from concentration inequalities. And then we find that that here, of course, uniform sampling doesn't give us any benefit. Stratifying by these very simple categories gives us very little benefit of about 1 seed equivalent. Manual stratification can actually do much better, and in some cases gives us more than 4 seed equivalents. And the clustering is closer to the manual stratification than anything else, but still falls short. We also looked at how the rounding and the variance introduced by rounding affects these results. If there was no rounding, this is what would be possible. And we have some ideas for how to improve both the manual stratification as well as the k-means inspired classification to get to achieve more of this potential and get the bars closer to that than to the way they're currently at. So, what do I hope that you take home from this talk? 3 things, I think. The first thing is maybe the most important one. That sortition is really cool. I really think that it's an exciting paradigm for democracy. I think it's really worth thinking about. I think that there's a lot of technical problems that must lie in there and that are really worth exploring. And I would love to have more of this community think about these problems. The second point is we often think about fairness and treating subsets of the population fairly, but often we assume that these groups are defined a priori. And everything that goes beyond that, I think, is very exciting. So, for example, groups that are defined fuzzily or guarantees that hold for all possible groups, such as in the previous talk, to me are very exciting because they allow us to describe richer ways of fairness. And yeah, I think they also often lead to very interesting technical problems. And then finally, if we want to combine these 2 things, if we want to work in sortition and we care about these somewhat undefined opinion groups, then stratification can really help. Thank you very much. I'd love to take some questions. Yes, please. No, so the very good thing is that we always preserve this property that every person is selected with equal probability, no matter which stratum they lie in. So if their utilities are risk neutral and are independent of whether other people are selected, there's no incentive problem. That being said, we're working in a framework where variances matter, and so it could be that one person, for example, cares about being on the committee only if many other people from their group are also on the committee. And then this might conceivably become a problem. Yes? Mm-hmm. I have to admit that it sounds very interesting. I don't really know yet what you're getting at. Mostly, yeah, what to do. So we can do the sampling and then we can get an estimate, say, for how large these groups are. But do we actually get to a committee from there? Yeah. Oh, interesting. I have not thought about that, but I would love to chat more offline. Yes. I'm not exactly sure whether I understood the question. I think so the parts of the stats literature that I read and that I tried to compare to for this paper and where I wanted to see whether it was applicable, many things very quickly were not applicable anymore because many things in stats oversample groups and then rely on the fact that they can weight these oversampled groups. Whereas if we actually want to select people, not just determine the ratio, but select real people, then we don't have this option of weighting. I think, to my knowledge, there's very little in the actual stats literature that's applicable. If you happen to know things, I'd be super interested.
All right, let's thank the speaker again.
Thank you.